Hello students, I am Dr. Tanmay Vishwas. I welcome you all in my channel Chemistry, the Mystery of Molecules. I hope you all are fine. So today we will discuss a multiple choice question or MCQ about reaction of phenol in presence of KOH and carbon dioxide under high temperature pressure, and second workup with concentrated dilute sulfuric acid. So the question of today's discussion is what is the major product of this reaction. So for that purpose, four options are provided in front of you and one of them is the right answer. So you have to find what is the right answer. So I first request you, please pause the video and try by yourself, because self-evaluation is essential for success in life, because if you understand your strength as well as weakness, it will help you to prepare yourself for the future. Fine. And at the end we will discuss another question. If the KOH is replaced by NaOH, will it be result in a same product or different product? So a lot of chemistry to be learned in this video, so I request you please watch until the end with peaceful mind and full concentration. So let's start. As well, so as usual, I first discuss about the nature of the reagent, because if you understand the nature of the reagent, you can solve any kind of problem. Okay, so first of all, first reagent is given, that is phenol. So this phenol is an aromatic alcohol, and this is actually more acidic than ethanol due to resonance stabilization of the corresponding O minus, means the conjugate acid you may consider. So phenol in presence of base, what it will be converted into phenoxide. Okay, so this is more acidic rather than simple alcohol like ethanol. Okay, the negative charge is delocalized over this ring. Fine. That is the reason. And actually phenol is activated nucleus. Fine, for aromatic electrophilic substitution. Now its activity further improves when it became phenoxide, because it already carrying a negative charge. So if it's carrying a negative charge, it is highly expected that the negative electron density in the benzene ring will increase, because the negative charge is stabilized by the delocalization on this O minus. Fine. Okay, fine. So this activated nature of phenol is further activated because of deprotonation, and activated means for aromatic electrophilic substitution. And actually this phenol or phenoxide both are orthopara orienting, and as I told previously, it's activating. Fine. Since phenol is more acidic than alcohol, so deprotonation could be achieved by the use of KOH as a base. Okay, so KOH is strong enough for deprotonation of phenol to produce the phenoxide under this condition. Fine. And this reaction here we are using carbon dioxide. So this is actually a carbon dioxide fixation reaction. And why this is important? Right now, you have already heard many things about global warming, climate change, CO2 emission, this. I know it's a very common news, as well as a global problem for our climate security. Okay, so why this is happening? Because every day we are burning ton of fossil fuel, and that produced carbon dioxide we are dumping in the atmosphere. That excess carbon dioxide is causing global warming as well as climate change. So utilization of carbon dioxide as a synthon or chemical for preparation of other chemical is essential, and that thing, one of the process you may consider this reaction where carbon dioxide is getting incorporated into the organic molecules. Okay, so carbon dioxide, if you look at this molecule, this looks this. So by nature this is an electron deficient molecule. Why? Because oxygen is delta minus, carbon is delta plus. So it is actually electron deficient, or you may consider electrophile. So what we are generating? We are generating a nucleophilic species or electron rich species, that is phenol to phenoxide. And if you under this high pressure and high temperature, it reacts with these electrophile. Why dangerous condition? Means high pressure and high temperature treated. First of all, this carbon dioxide is a stable molecule, thermodynamically as well as kinetically stable. Second, it's a gas, so pressure is needed to bring the gas into the liquid reaction mixture. So that's why under this condition they reacts. So how they reacts and what is the product, let's discuss. So as we told that in terms of KOH, phenol is converted into phenoxide. Fine. So this is more activated for aromatic electrophilic substitution, and two positions are available for AES. That is, this is the ortho and this is the para. And we know generally para attack is more favored over ortho. Why? Because in case of para, just look, it's a para-benzoquinonoid derivative, but in case of ortho, what is expected? That this is an this is an orthobenzoquinonoid derivative. Okay, so this part, and we know para-benzoquinones are more stable than ortho one, but this is possible if there is some chelation effect. Okay, I'll come. So chelation effect result. So what happens? This first carboxylic acid in formation. After that, this proton is abstracted, because after this proton abstraction, this electron goes here, comes here, and so aromaticity is gained. Means what happens here? In this case, it first converted into O minus phenolic derivative. Then after protonation, what it resulted means for this acid and this potassium salt of carboxylic acid, and after further protonation using this sulfuric acid was resulted in this para-hydroxybenzoic acid. So this is para-hydroxybenzoic acid. Fine. Now what happened in case of ortho? What is the chelation effect? See, so this is the O minus, it's remain closer to Na plus in order to maintain the electro neutrality. So what happens when you put carbon dioxide? This carbon dioxide also come closer and it can coordinate with the sodium plus. Fine. And this so through this coordination reaction happens, and what it produces? This produces this double bond O, there is one hydrogen, there is C, so after attack it will open up, CO minus double bond O. Okay, and in this case, after means aromaticity gaining, what it resulted? It resulted at first of all aromaticity gaining, and second is reaction with dilute sulfuric acid. This is so here this is a para-hydroxybenzoic acid, and in this case what we get? Ortho-hydroxybenzoic acid, or it has another common name, that is salicylic acid. And this salicylic acid has a very good property, that is it is actually a painkiller by nature, or methyl salicylate, that is oil of wintergreen, that is also, or another conversion of salicylic acid, that is orthoacetyl salicylic acid, that is aspirin. Okay, means what do I mean by the structure? I think you should know. So this is salicylic acid OCOCH3. So this is aspirin. It is also a painkiller as well as medicine for heart disease. So lots of application of this carbon dioxide fixation. I have already uploaded a dedicated lecture on aspirin, you may visit. So from this thing we have learned what? That changing a metal ion, that is potassium or sodium, the selectivity of product completely changes. Why chelation cannot happen in this case? This is because the larger size of potassium doesn't allow the chelation. Okay, because it's the transition state, you can see here, it's a ring type in nature. So if one atom is very large, then formation of ring is difficult, so reaction cannot happen. Fine. So answer of our today's question is para-hydroxybenzoic acid. Okay, and what happened if KOH is replaced by sodium hydroxide? Then the answer will be ortho-hydroxybenzoic acid or salicylic acid. Okay, so please keep this information clearly. I have explained, try to understand, and if you didn't get, please watch it again. I believe you can understand. Fine. So in conclusion, what we have learned today? We have learned that phenol to benzaldehyde, this is benzoic acid conversion is achieved by QH and CO2. Point number 1. Second, the orthoisomer, that is salicylic acid, could be prepared by simple replacement or change of KOH with NaOH. Fine. And this reaction is named as cold-base-meat reaction. Okay, this is a kind of CO2 fixation reaction through aromatic electrolytic substitution under high pressure of the CO2 gas. Fine. And most importantly, phenol is an activated nucleus and it's orthopara orienting due to the plus R effect of the lone pair of oxygen, okay, and its reactivity could further be enhanced by deprotonation of the OH group. And similar property you can observe in case of aromatic electrolytic substitution of pyrrole. It is highly activated electron rich, but if you put any base, for example this, then base tuned aromatic electrophilic substitution you can see means higher reactivity, means after deprotonation it became further. It was similar kind of property you can observe, and I have already uploaded a lecture about property of this thing of pyrrole, so please visit for better understanding. Fine. So this is the end of this discussion. I believe you have enjoyed the video. If it is really, then please press the like button and write your opinion in the comment box. And most importantly, if you think this video is worthy, then share it with your friends. And if you think my channel is providing good content, then please subscribe my channel Chemistry the Mystery of Molecule and press the bell icon to get the notification of every new single video I upload. Most importantly, before going, thank you all for watching this video and stay happy, stay blessed. See you in my next video. All the best.